omega L squared. And over there, the whole thing will be equal to 100 times 10 to the power 6. So if we're going to drop, or we're going to remove the square root so that it's easier to solve, we have 158.519 omega L squared, and this will be 100 times 10 to the power 6 squared. Okay. So now the problem with this equation over here is this. Okay. You have one equation and you have two unknowns. Okay. So if I were to expand this, I will get 5.70.79 squared is equal to 5.011 times 10 to the power 3 omega squared L4 plus by 158.519 squared again is 25.128 times 10 to the power 3 omega squared L squared, and then what we have over here is 100 power 6 squared is equal to 10 times 10 to the power 15. Okay, so this is our equation. So you will see that one equation, two unknowns, and the term over here, you have omega squared L4, you have omega squared L squared. What we are trying to do over here is to determine what? So if we go back to the question, we are trying to determine omega. Okay, and we know omega is related to the length. So if you look at the question, or if you go back to the figure, right, depending on what this length is, it will affect our omega. So if you look at the question, there is no length. Okay, the length is not specified. Okay, what we want to find is omega. So for this case, when you come to a problem like this, okay, it's not unsolvable. The next thing you have to do is you're going to assume, okay, we're going to assume a L value. Okay, we're going to assume a L value. So for this case, I'm going to assume, okay, L is equal to 2 meters. I'm going to make that assumption. And once this assumption is made, you have to declare it. So we are going to declare that L is equal to 2 meters. You can also say L is equal to 1 meter, no problem. Okay, so once you declare L is equal to 2 meters, then you can determine your what? Omega squared. Okay, so once we declare L is equal to 2 meters, so 2 power 4 times by 5.011 power 3 is equal to 80.176 times 10 to the power 3 omega squared plus by 2 squared times 1. So 100.512. This will be equal to 10 times 10 to the power 5. So now you realize that, hey, we can have a solution now. Okay, so omega is equal to square root of 10 times 10 to the power 5, not 5, 15. I do apologize. Okay, not 5, 15. And then this whole thing, we're going to divide by 80.176 power 3 plus by 100.512 power 3 is equal to 180.688. Times 10 to the power 3. So omega be 10 power 10 power 15 divided by 180.688 power 3 square root, and it's going to be equal to 235.253 times 10 to the power 3 Newton per meter. So we have determined our omega already. Okay, so this omega is based on the maximum shear stress criteria. Okay, so now I'm going to go back to this circle over here. I'm going back to this circle over here. Okay, so what we have just done is we let tau max to be equal to 100 times 10 to the power 6. Okay, so what we have just done is we have put an upper limit, okay, or we have put a shear limit. Okay, let me elaborate. So I'm going to draw in red now. I'm going to draw in red. I'm going to make the marker thick. So now we have put an upper limit on shear and also a negative shear, okay, at the bottom. Okay. So this is our 100. This is our 100 times 10 to the power 6. 100 times 10 to the power 6. One is positive, the other one is negative. So the mole circle that we have drawn, that is the biggest diameter. Okay, it cannot be any bigger than that anymore. I see a question from someone. Lee.
Sir, can you explain why maximum shear stress is equal to 100 times 10 to the power of 6?
Because over here, we are applying the maximum shear stress criteria. Okay, it's because we apply the maximum shear stress criteria is a stress yield divided by 2. Okay, so that's why.
How did you get where did you know this criteria?
So this criteria is basically the yield stress divided by 2. That's it. It's a very simple formula.
So we just need to remember it, right?
Yes. Or I
Oh,
can not I don't think you can remember it. I mean, it's very easy. I'll provide on the formula sheet.
okay, thank
Okay.
you.
Okay. So from here, right? So we have, coming back to where we are now, we have identified that this circle, the upper and lower bound. Okay, so the circle cannot go outside this red line, which is at the top and at the bottom. The next thing we have to check now, right? We have to check that we have to now also ensure that the maximum shear stress, okay, the maximum the minimum stress, which I'm going to draw a line now. Okay, the minimum stress over here. Okay, this minimum stress over here. Okay, so I draw over here. So this over here, we know that it's given to us that this is equal to minus 200 times 10 to the power 6. We have to now determine what this value is. Okay, if this value is less than 200, if stress mean, okay, is less than, or if stress mean now, let's see later on when we calculate, it's going to be minus 250 times 10 to the power 6 Pascal, the structure will fail. Okay, there's no point determining factor of safety when the structure fail. We have to make sure that it's greater than minus 200 times 10 to the power 6. Okay, so for now, we know that omega is equal to 235.253 times 10 to the power 6. Next thing that we have to do now is we have to determine what is our stress minimum. Okay, we have to determine value of stress minimum. Okay, so we know stress minimum is equal to stress average. Okay, so it's equal to the stress average, right? Stress average minus, is equal to stress average minus by the tau max. Why minus? Because we know that this is our stress average, right? And the tau max is our radius. So we have to now calculate. We know this value, and this value is our radius. Okay. So from here, the stress average will be equal to minus 70, right? So this will be equal to, so stress average over here, I'm going to use this equation over here. So minus 70.79. Then we are going to multiply by our omega, which we found, 235.253 times 10 to the power 3. And then the length squared is going to be 2 squared. Okay. And then we're going to minus the tau max, which is 100 times 10 to the power 6. So this value will be equal to minus 70.79 times by 235.253 power 3 times 4. So minus 66.614 times 10 to the power 3 minus, sorry, times 10 to the power 6. Yeah, times 10 to the power 6 minus by 100 times 10 to the power 6. So this is equal to minus 166.614 times 10 to the power 6 Pascal. So we realize that the structure will not fail because the stress minimum is greater than minus 200 megapascal. Okay, so structure will not yield, and this is because the stress mean is, or this is because the stress mean is equal to minus 166.614 times 10 to the power 6 Pascal, which is greater than minus 200 times 10 to the power 6 Pascal. Okay, so therefore, the factor of safety will be equal to 200 or minus 200 times 10 to the power 6 divided by minus 166.614 times 10 to the power 6. So 200, 166.614 power 6 is equal to 1.2. Okay, that is the factor of safety. So as you can see, a question like this, I want you all to see from the introduction what is the expectation. You can see the layers of information that you need to acquire. Okay, so I can strongly tell you that if you were tasked to design a structure like this, okay, the mandate that I'm going to do for all of you is you are capable of designing or selecting the material for this structure together with calculating the factor of safety. Okay, and the as you can see, the the integration of different topics is why this course is not so straightforward. Okay, let me elaborate. So what do I mean integration of different topics? Same course, but different topics. So what the first thing, so if you look at the example that we have started on Tuesday, you need to understand, or you need to know, okay, how this data from a material handbook is acquired. Okay, you need to understand it. Okay, because we are going to calculate factor of safety, or we are going to determine what material to use. So you need to know. And we all know now they are from uniaxial test, and we also know what that all these value. Okay, in fact, these values over here are your what? Principal stresses. Now you know why already, right? Because they are carried out in one directional. And then you also know that if you're not given the shear value, what you can do, just divide by 2. Simple assumption or straightforward assumption or easiest assumption. Then the next thing is what formula to use, okay? And you have to be aware that a structure like this has a combined loading of normal stresses. Okay, we have a combined loading of normal stresses, and we have a combined loading of shear stresses. What is being tested is only what? Unit axial. So how can we select material when the loading is not the same like how the material has been tested? You have to go to Mohs circle. Okay, and then we learn about maximum shear stress criteria over here, right? So this will be equal to the maximum shear stress is stress U divided by 2. When to use what for calculating factor of safety? If it's a brittle material, you use the ultimate strength, okay, because the ultimate strength and U strength for brittle material is about the same. Whereas for ductile, you have to use what? U strength. Why? Because the U strength is so much lower, not greater. I make a mistake down here, okay? It's lower. Too excited. Okay, the U strength is lower than the ultimate strength. Then from here, you have to remember from your static and strength of material how to determine the